Welcome to our lesson today in preparation for College of Nursing Sciences entrance exam and interview. Today, we are looking at physics. And under physics, we are starting physics with the first topic, units. And under units, we are looking at fundamental units. That's the F unit. All right. First of all, we have to understand the meaning of fundamental unit. However, we have other types of units, such as derived units, fundamental units, and derived units. But before we look at fundamental units and derived units, let's first of all understand what is meant by a quantity. All right, a quantity. A quantity means something that can be measured, something that can be quantized. That's the meaning of quantity. What it means is that the thing can be measured. So in physics, because physics deals with the physical, what we can see, we have physical quantities. All right, physical quantities. Okay, so physical quantities are things that can be measured that are visible, tangible things that can be measured. That's physical quantity. All right, so when we go back to fundamental units is the units. That's what we use to measure physical quantities. They are called the basic units. All right, they are the basic of measurement. All right, they are known as the basic unit, the foundation of every other unit. See fundamental unit as the unit that gives birth to every other unit of measurement. Like I said, unit is what we use in measurement in physics. Remember, physics deals with mostly the physical, what we can observe with our eyes. That's why we have physical quantities. All right. So since they are the basic unit, it means that they are the mother of every other unit. So every other unit are born from the fundamental unit. Units such as derived units, they are all derived from fundamental units. As simple as that, A, B, C, D. Now, let's understand the list of the fundamental units, which is the basic unit. All right, the first one we have is length. We have length. All right, we have mass. All right, we have time. Length is usually measured in what? In meters. All right, mass is usually measured in what? In kilogram. All right, then time is usually measured in what? Seconds. All right, we have another one. We have other ones like luminosity or luminous intensity. All right, luminous intensity measured in what? Intensity, measured in candela. All right, measured in candela. We have other one like temperature, measured in Kelvin. All right, this is the standard. Temperature can also be measured in degrees Celsius, but the standard is Kelvin. Take note of that. We have amount of substance, which is measured in mole. We have electric charge measured in coulomb. Let's use I as charge, measured in what? Coulomb, C, or coulomb. All right, coulombs. All right, C. So electric charge measured in coulomb. Then we also have amount of substance. All right, that's the amount of substance. You know chemistry now. Amount of substance measured in mole. All right. So these are the fundamental units used to measure physical quantities. They are the basic units used to measure fundamental physical quantities. So these quantities here are known as the fundamental physical quantities. 1, 2, 3, 4, 5, 6, 7. But the most important fundamental physical quantity, which is very important in dimension, is length, mass, and time. Okay, that's length, mass, and time. They are the three most important fundamental physical quantities normally used in dimension. Now, let's look at derived units. Derived units. Like we said before, that after looking at fundamental units, derived units are the units that are gotten from the addition of fundamental units. When you add some fundamental units, you get derived units. So fundamental, fun plus fun, gives you what? Derived. All right, derived. As easy as A, B, C, D. All right, it's very easy. So we see something like area. Remember, the derived unit is used in the measurement of derived quantities. All right, use the measuring derived quantities. All right, remember they are derived physical what? Quantities. Derived physical quantities. For example, measuring area. For example, area is measured in what? What's the unit? Meter square. All right. Area measured in meter square. All right. Then we have volume, we have weight slash force, we have speed. So volume is measured in what? Meter cube. So understanding this, remember we said the addition of fundamental units gives us derived units. So m plus m gives us what? Sorry, m times m gives us what? M squared. All right, m times m gives us what? M cube, right? So that's how we got the derived units. All right, we also have weight. Remember that weight is also force, right? So the unit of weight is usually Newton, or it can be representing kilogram, okay, which is mass, kilogram, meter, second raised to power 2. All right, so this one is, the pair is here. So kilogram per meter second raised to power 2. All right, that is the SI unit. We also have we've done volume. All these are derived units, okay, derived quantity, and these are derived units for measuring them, addition of 2 or more. We also have speed. All right, speed, which is what? Meter per second. All right, meter per second. We also have velocity, which has what? The same unit as what? Speed, meter per second. All right, so having understood this, let's quickly go to measuring instruments. What are measuring instruments? They are instruments or equipment used in measurement. We use them to measure quantities. All right, since we are dealing with physics, what are we measuring? We are measuring physical quantities. All right, so the first one here is meter rule. All right, measuring of what? Length. Let's just put it length. All right, measuring length, we can use meter rule. 1. 2, we can use tape. All right, we can also use tape depending on what we are measuring. If you are measuring more than, let's say, 5 meters, we are supposed to use tape, because meter rule is short. All right, we use it for shorter lengths. Okay, when the length is longer, like measurement of land, so we can now use tape. Or when we are measuring something that's longer than 5 meters, or sometimes even 2 meters self. All right, 2 meters, you can't even use meter rule to measure again. All right, so we use tape for longer length measurement. All right, so what's the next? You can also measure length with the caliper and micrometer screw gauge. All right, vernier caliper. All right, the scale is usually in centimeter. All right, centimeter, that's the scale, and we observe zero error of about 0.01. all right, measured in centimeter. You must observe this zero error when you are using the vernier caliper. We also have number 4, we have micrometer screw gauge. All right, micrometer screw gauge, used to measure what? Length. All right, smaller lengths, those tiny minute lengths like the hair, okay, or wire, 18 wire, you use micrometer screw gauge. Okay, bigger length, you can use vernier caliper, especially when you are measuring a holo, the diameter of a holo. Vernier caliper is usually used to measure diameter. Micrometer screw gauge, still measurement of diameter. But when you have a holo object to be measured, you want to measure the diameter of this place, you are going to need a vernier caliper, okay, because you are going to use the internal jaw of the vernier caliper like this, so that the internal jaw sits inside the hollow part. The vernier caliper also has the external jaw. That's if you want to measure the external diameter. All right, maybe you want to measure the thickness of a cylinder. All right, you use a vernier caliper. All right, then for smaller measurements, you use micrometer screw gauge. All right, so measurement of fluid, we use what? We use measuring cylinder for fluid. All right, or fluid volume. All right, we use measuring cylinder. We use measuring cylinder. All right, we use measuring cylinder for fluid. Then for weight, when measuring weight, what do we use? We use, first of all, let's talk about mass first of all before we look at weight. Measuring mass. All right, when we are measuring mass, we can use beam balance. All right, or the balance. All right, most of the balance apart from spring balance. We can use beam, we can use top pan. All right, we can use chemical balance. All right, beam, top pan balance, chemical balance, all these balances, we can use them to measure mass. All right, then when we want to measure weight, what are we going to use in the measurement of weight? We use spring balance. All right, spring balance, and also we can use scale. All right, measuring scale. All right, remember that weight is force. All right, what is mass? Mass is the amount of matter contained by a body. The magnitude of a body is known as what? Matter. All right. So what next? Time. Time measurements. We use what? Stop clock. Stop what? Clock. Or stopwatch / wash. All right. So that's that for that. All right. So we have to proceed to the next. Proceeding to the next. So when measuring length, volume, and surface areas of bodies, there is something we have to consider. If the body is regular or the body is irregular, that is one of the things we have to consider when measuring the volume, the surface area, and also the length of various solid. Is it regular? For the regular substance, this one is for the irregular. All right. So for the regular, what do we apply? If the shape of the substance is regular, measuring the volume, we can use the normal instruments for measurement. All right. Like we can use instruments for measuring length, instruments for measuring volume. Like length, you can use meter rule here, meter rule. For volume, you can use measuring cylinder. All right. Measuring cylinder. All right. Okay. So just know that you use the standard unit here. All right. And you use the measuring instrument for regular shaped solid when the shape of the solid is regular. All right. Let's just put shape here. All right. Shape. All right. Then when we have an irregular shape, the shape is not regular. Abadabidi shape, you can't give a name to the shape. For example, we are measuring something here. We already know that the shape is a rectangular shape, or it has a cylindrical shape, or trapezium shape. All right, or cube shape, cube or cuboid shape, whatever. All right, we know the shape is regular, all right, or is round. But irregular shape has no definite shape. How do we measure their volume? How do we do that? We do that by immersing in water, all right, following what? Following the Archimedes principle, all right, Archimedes principle. Archimedes principle. All right, so we measure it by what? Immersion in water. You immerse it in water. The amount of fluid displaced is weighed to know the what? The volume of the whatever object we are measuring or whatever body we are measuring. All right, using what? The amount of fluid displaced. All right, to measure volume. All right, so when you immerse it in water, maybe this is the object, irregular shape. You immerse it in water. This is a beaker of water. All right, the amount of fluid displaced, all right, is usually weighed to get the volume. All right, as easy as that. A, B, C, D. All right, so let's move to the next. SI unit. SI unit. SI unit is simple. See SI unit as a standard for measurement. All right, I am going to give you a very practical example. For example, we have mass. All right, mass can be measured with, or it can be measured in gram. All right, mass can be measured in gram. It can also be measured in kilogram. All right, but SI unit says there is a standard, something that is widely acceptable, a unit that is widely acceptable for measuring a physical quantity. All right, and what is that unit? It's called the SI unit. All right, and what is the full meaning of the SI unit? It means the what? The systemic international unit. All right, the systemic international unit, widely acceptable, globally acceptable for the measurement of a particular physical quantity. So you have to know them. You have to know them. For example, that of length is meter. That of mass, you can see mass can be measured with gram, mass can be measured with kilogram. But how do we choose the one that is standard? Through the SI unit. And the standard unit of measuring mass is what? Kilogram, kg. All right? That doesn't mean that mass can be measured in grams. So you have to understand the SI units. So the time measured in second. So these three are the fundamental, the most important fundamental physical quantities and their units. All right? As simple as that. So we are going to look at more, SI units of derived quantity. For example, you have derived quantity with your unit like for velocity, meter per second. For speed, you have meter per second. For force, you have kilogram per meter second square. You have for acceleration, you have meter per second square, and so on and so forth. Okay, you can measure pressure, the SI unit of pressure. All right, SI unit, that's the standard unit, is Newton per meter square. Remember, pressure is the what? Is the force exerted per what? Per area. Force exerted per area. All right, force exerted per area. The area, all this force, this one is pressure. So the force exerted on the area is pressure. Okay, the definition is slightly closer to the one of density, but there's a little different because this one deals with the area. All right, the area. The force must come in contact with the area. So Newton here for force. All right, the meter square here for the area. All right, remember the SI unit of area. Pressure can also be measured in what? Pascal, but this is not the standard. This one is the standard derived SI unit for pressure. But pressure can also be measured in Pascal, PSI. All right, moving on to the next, we are looking at dimension. Straight up, dimension. Dimension is a very easy thing in physics. It is very easy. In fact, dimension is one of the easiest topic in physics involving calculation. Trust me, it's one of the easiest. How do we do dimension? First of all, we have to understand what dimension is. What is dimension? What is dimension? Dimension in physics. Dimension. All right. Dimension says turn a derived unit to fundamental units. All right. Or turn a derived unit to fundamental quantities. Use fundamental quantities to represent a derived unit. What are the key fundamental quantities? Those three key fundamental quantities, like length, which are what? Length, mass, and time. All right. So these three. Turn everything correspondingly to this length, mass, and time. That is dimension. That's what dimension is all about. When you want to do dimension of any physical quantity, what you have to do first is you have to define the physical quantity first. After defining the physical quantity, you write out the formula of the physical quantity. After writing out the formula of the physical quantity, then in the formula helps you to write out the SI unit, the derived unit of the physical quantity. Then you use that derived unit of the physical quantity to convert all the the units in it to the corresponding fundamental physical quantities here. All right. The one that is involved with distance, you change it to length. The one that is involved with mass, or that involves mass, you change it to m. The one that involves time, you change it to t. Now, let's do an example illustrating what I just explained. All right. Let's say find the dimension of velocity. All right. What is velocity? Velocity is usually the change of rate of what? Displacement. All right. Displacement. Delta displacement. What is displacement? Displacement is usually what? Is usually distance, right? Distance moved in a what? In a specific direction. That is displacement. Since we are talking about change of rate here, change is indicated here. The change of rate of displacement, meaning that time must be involved. So the SI unit of velocity is meter. Remember, displacement is length, and length is measured in what? Meter. So meter per. Remember, time is involved. What is the SI unit of time, or the unit of time? Unit of time is seconds. So this is the SI unit of displacement. Now let's find the dimension. It's very easy. M here represents what? Length, because it's what? Meter. So we change it to what? L. S here represents what? S represents second, and it represents what in the fundamental unit? It represents time. You put it here, time. All right, or you put your power. Okay, so this is the dimension of velocity, L per t. All right, but because of algebra, sometimes you can see it as L raised to power minus 1 / t raised to power minus 1. Is correct. Remember the law of algebra that any letter represents a number, and it is what? Inherently having raised to power minus 1 or raised to power 1. All right, that is algebra for you. So if you see it like this, raised to power 1 or raised to power minus 1, it is still correct. They are all similar. All right, so let's quickly look at another example of another dimension. Then I give you some other dimensions for you to go and do. All right, I give you some other dimensions for you to go and do, to practice. This is a very common question in College of Nursing Sciences entrance exam. And before I continue, please have it in mind that there are so many fake past questions. College of Nursing Sciences past questions. You have so many fake. They are not any College of Nursing Sciences past question. 98% of the College of Nursing Sciences in Nigeria never release their past questions. You can never see their past questions. I don't know why. That is the way College of Nursing believe. You know that College of Nursing is like a paramilitary. All right. So beware of fake past questions. All right. So you might have the school's heading on it, but definitely it might not be the past question of that College of Nursing Sciences. Maybe they just sued it to you to prepare with. All right. So let's say we are asked to find the dimension of acceleration. All right. What is the definition of acceleration? Is the change of rate of what? Velocity. All right. Since velocity is given as meter per second, and we are told that acceleration is the change of rate of what? Meter per second. Remember, I said anything that involves change of rate is time that you are going to use to differentiate the change of the rate of the velocity or acceleration. All right. So because time is involved, one more second is going to be added as time. All right. So the SI unit of acceleration is meter per second square. All right. So looking for the dimension, we have to convert it to what? L. Remember the fundamental quantities. We convert it to this. M here stands for meter, which is length. We change it to L. M. S here stands for time, and it's having to the power of 2. So what do? Time, S here is second, right? And it stands for time. So we put it as T, right? And we put it raised to power 2. This is the dimension of acceleration. But we can also rewrite this as like this. Remember algebra, raised to power minus 1. According to algebra style, you can see it like this in your option. All right. So just beware that any number or any letter, no letter represent number according to algebra, raised to power minus 1 is the same thing because it has this invisibly or raised to power 1. All right. So that's that for that. So I'm giving you an assignment. Do the dimension of force, energy, and density. Do the dimensions of force, energy, and density. So that's that for your assignment. Now, let's digress to the next. We have to understand what is meant by homogeneity of equations. Homogeneity of equations. Homogeneity of equations. Homogeneity, homo, then geneity. All right. Homo means same or one. Two of us, we are the same or we are one. All right. That's homo, the meaning of homo. Geneity. Geneity means generation. All right. Generation or origin. All right. So it means prove homogeneity of equation means that prove that the equation has the same what? Origin. Both sides of the equation have the same origin. That is homogeneity of equation. How do we prove that? For example, we have in every equation in physics, we have left-hand side of the equation. All right. Since we are using this board as a sample, here is the right side of the board. Here is the left side of the board. So we are going to put here as the right-hand side of the equation. All right. Then here's the left-hand side of the equation. All right. So let's say we use this equation, the second equation of motion, S equal to ut plus 1/2, which is half at squared. All right. So this one is the value. All right. This is the value. All right. So let's just keep this away because it's the value. All right. So this is the right-hand side of the equation, and this from here is the left-hand side of the equation. What is the demarcation? The sign. Either you have a plus sign or you have minus and so on and so forth. All right. So the sign demarcates the right-hand side and the left-hand side, and we have plus here as the sign. All right. So what does the homogeneity of equation want? What do they want you to test when they say test for homogeneity of equation? They want you to ensure that you have the same fundamental physical quantities on both sides of the equation. All right. So what are the fundamental physical quantities? We have length, we have mass, and we have time. All right. So these are the fundamental. So if this equation is dimensionally homogeneous, that means that we are going to have these fundamental physical quantities in common. That's we are going to have it on the right hand side of the equation and also the left hand side of the equation. Now, let's look at that. Let's figure out if this equation is dimensionally homogeneous. All right. So here, this one is the value and this is distance, right? Represent distance. And distance in the fundamental physical quantity is represented as what? Length. So we can rewrite this equation as length is equal to what? U is what? Initial velocity. And velocity is what? Mostly what? Length. All right. But since we are using the SI unit of velocity, meter per second, so we are going to write it as length, and what? And time. All right. Meter per second. Length for meter, t for second, which is time. Then we put our plus that demarcates the right hand side from the left hand side. All right. What do we have here? 1/2. Then we have A. What is A? A is acceleration. What's the unit of acceleration? Meter per second square. Meter stands for what here? It corresponds with what here? Length, right? We put L. Then what of second square? The second square is what? Second square is t. It corresponds with t. Second is time. Correspond with t. That's t square, right? So what do we have last here? We have another t square. All right, t square. All right. So we want to figure out if the equation is dimensionally homogeneous. So, like I said, you have to have a matching fundamental physical quantity on both sides, the left and the right hand side, for the equation to be what? Dimensionally homogeneous. All right. So here we have LT. So LT is common. On the left side of the equation, we have LT. So we have L and T there. On the right side of the equation, what do we still have? We still have L and T. So we have L and T on both sides. So that shows that what? The equation is what? Is dimensionally homogeneous, of the same origin, L and T. But let's say here we have only L and here we have only T. It means what? That the equation is not dimensionally homogeneous. As simple as that. So look out for other equations and, check if they are dimensionally homogeneous or not. All right. So that's your second assignment on this homogeneity of equation. This question is a very recurrent question. So I hope you understood this aspect. It's very easy. All right. I'm going to make it very easy. Now we are looking at the limitations of measurement. What are the limitations of measurement? Of course, with measure, yes, there must be limitations during measurement. All right. What is limitation? Anything that prevents you from achieving what you ought to achieve or what you plan to achieve. All right. It's like a barrier. So what is the limitation of measurement? Errors. Humans can never be perfect. It is impossible. All right. So the error, because of the errors in measurement, most of the time we deal with this with calibration. All right. So because of errors, we will now use calibration. All right. To bypass errors. All right. So we are going to look at types of errors right away. All right. First of all, we start with the fundamental one, followed by the one we get from measurement. All right. So looking at the fundamental error, we have the first error, types of error. We have systematic error. The systematic error, this one is an error due to what? Due to the system itself. All right, the system setup, the system, what the system is made up of. Okay, what is made of? All right, the setup. Did you follow the rules and regulation? It's an error that is caused by not following the rules and regulation of the particular measurement procedure that you are carrying out. Systematic, you didn't follow the system or the system setup itself. Setting up the system. For example, we want to use a vernier caliper to measure. All right, we want to use a vernier caliper to measure, and we are having issues setting up the system properly. All right, we are having issues setting up the system properly. For example, the entire system of the vernier caliper can cause systematic error when the system is not functioning properly. Maybe the jaws are not functioning properly, the screw clamp are not functioning properly, they are faulty, or during the measurement, you didn't follow the systematic procedure of using the vernier caliper. For example, you didn't tighten the jaw properly during your measurement. So that's what? Systematic error. All right. Let's look at the second type of error, which is known as erratic error. Number 2 is erratic error. All right. Erratic error is what? Related to what? Unpredictable. Unpredictable factors. All right. It can be related to unpredictable factors also also related to faulty equipment. All right, faulty measurement equipment. Maybe you are measuring something now because the equipment is a bit faulty. You are finding it difficult to get stability during your measurements. That is an erratic error. Then number 3, let's look at random error. All right, random error is from something random. All right, maybe you are measuring and you see air resistance. All right, air resistance puts some, some abnormalities in your measurements. For example, environmental. This one is related to environmental objects or events. All right, objects or events. All right, interfering with measurement. All right, usually you will have to measure 2 times. When you measure 2 times, the first result will be different from the second result. The second result will be different from the third result. So that tells you that it's a what? It's a random error. All right, then let's look at the 4th error, which is known as the zero error. All right, zero error is due to what? The zero mark. All right, due to the zero mark. So I have to align myself at angle 90, stand like this in front of it, align myself properly to the point, and read the ruler. Show what zero error is known for and why it is called the zero error. All right. So for the zero error, when you didn't put, we have the zero mark in the meter rule like this. Let's say here is the zero mark. So let's say when you are measuring, you didn't start from the zero mark during your measurement. Okay, you shift it slightly a little bit. And usually, because of this error, we usually use what? Calibration of what? 0.01%, 0.01 centimeter or 0.01 millimeter as what? The ratio of error. All right, the ratio of error or the margin for error. All right, let's call it error margin during measurement of smaller lengths, because this error usually occur when we are measuring smaller lengths. All right, like the diameter of a thin wire and so on and so forth, the diameter of the hair, and so on and so forth. Let's look at the 5th error, which is parallax error. All right, parallax error. Parallax error is as a result of the measuring technique. All right, you are not following the measuring technique. You are not following the instruction of the measuring technique. For example, you are not looking the zero mark at angle 90. You are not looking it straight. Maybe you are using a meter rule, for example. You are using a meter rule to measure. I can't put a meter rule here attempting to measure like this. I will not stand here and be looking at the meter and tell you that it is 4.2. It is 4.2 centimeter. No, and that's going to alter your reading. Such error is known as parallax error. All right, parallax error during measurement. All right, as a result of your inability to properly handle measuring instruments. All right, following the rules of the measurement. I just give you an example where we have parallax error. Then we have the final error, number 6, which is gross error or human error. All right, this error is due to human activities. That's gross error. Maybe I might be here now trying to measure the length between here to here with a meter rule, and while I'm measuring, fly just perch on my ear, my external ear, and disturb me a little, and it shakes my hand during the measurement. An error must have occurred, and such error is known as what? Gross error. Gross error can also occur due to human negligence. All right, when human commits negligence, all right, you neglect during measurement, you can also have what they call gross error, or gross error is likely going to occur during such measurement. All right, having understood this error from the basic level, let's now look at the errors that we are bound to see after taking our readings. All right, after taking the readings, now the error that we are bound to see. So this one is post. After all these errors that we have just talked about, the errors that we are bound to see, okay, while we are comparing our reading. All right, the first error is called the absolute error. All right, and this absolute error is usually your you minus your true, okay, what you have measured, your value, the value you measured. Okay, let's say measured value. measured value minus true value. Okay, what is true value and what is measured value? Measured value is the value you got. Okay, the true value is the value that is supposed to be. So that is how you get your absolute error. All right, let's say for example, the measurement of the length of this board, all right, is supposed to be 20 centimeters. All right, that is what the true value. All right, so and while I measured, because of faulty equipment and all of that, or whatever error I experienced, okay, it could be systemic error, it could be erratic error, and so on and so forth, and I got 18 centimeter. So what am I going to do? I'm going to minus my measured value from my true value. All right, so my measured value is this one, which is this one is what I got. This one is the true value. So my measured value is 18 centimeter minus 20. All right, that is going to give us minus 2, right? So that is the absolute error. All right, now let's look at the second type of error after measurement, which is what? Relative error. All right, relative error is where you relate everything, you now do percentage. All right, relative error. How do we find relative error? Normally we use absolute error over true value times 100 over 1. Absolute error over true value times 100%. You can either decide to put over 1 or you leave it out. All right, times 100%. Okay, so let's say this is our absolute error, which is minus 2. We are looking for relative error. Then the true value is what? Over 20 times 100%. So what do we get? If we do minus 2 times 100, we are going to do is going to go with the one of the big one, right? With 100, which is plus, right? We are going to have minus 2 times 100. We are going to have 200 over 20. All right. Then we are going to have 10 as our relative error. All right. Is that clear? So during measurement, it is also important that we convert to significant figures. Yes, the most common is usually 2, 3, and 4 significant figures. That's the most common in physics. Okay, what is meant by significant figures? What they taught us in maths now, just represent it with 2, 3 significant figure. Okay, and so on and so forth. 2, 3, 4 significant figures. Okay, represent your answer in that. Then we also have standard form too. All right, standard form. The formula of standard form, which is 10 raised to power n. All right, where 10 is usually the standard, and we have a here as the significant figure or whatever. Right, so a times 10 raised to power n, or to the power of n. So let's say we are giving a number in decimal 0.00056. For example, I want to convert this to standard form. The first thing we do is what? The significant figure, which is this a. All right, we turn this to significant figure. We take what? 5 and 6. We now use points. We put points here. 5 what? 0.6. Then we put times 10, right? Times 10 raised to power n. What is the number of 0? Or the number 1, 2, 3, 4. So raised to power minus 4, because it's 0 points. Okay, you have 0 before points. We put minus 4. All right. So if we want to turn this one back to decimal, you can just put the 40 now, starting with 1, then point 1, 2, 3, then our 5, 6. Okay. So let's say here we don't have minus. Here we don't have minus. How do we convert this to decimal? Okay. What do? We just have to move this point here and replace the rest with the 0, right? So we are going to have 5, 6. We already moved the point. All right. So we replace the rest with 0. Remember, we have the point here. So we are not going to put 0, 0, 0 until it completes 4, right? 1, 2, 3, 4. Okay. So we are having 56,000. All right. In number. So expressing it in number. So this one is not decimal. Okay. It's in number, in figure, expressing in figure. All right. So when you are using standard form to solve, maybe you are giving various standard form and it's confusing you. Okay, if it's confusing you during the calculation because you have too much standard form in the calculation. Usually, when you are solving with standard form, it's not hard. Just use your minus or your plus times minus stuff. Just do it. Where you have raised to power minus, where you have raised to power minus, or where you have times. All right, maybe you have this standard form 5.6 times 10 raised to power 4. Then you have times here. Okay, you can see times 2.1 times 10 raised to power minus 2. Okay, so because you have times here, what are you going to do? 4, remember in indices, times turns to what? Plus. So you just put brackets to calculate the one you have on top. 4, this one is what? Times, right? So 4 times, we turn it to plus because of indices. 4 plus, okay, minus 2. Minus 2 will be in brackets. You see? As simple as that. So this is what you are going to have. You are going to do, of which you are going to do plus times minus, give you minus. So you do what you are supposed to do to get your what? 2. So that gives us 2. So we already have raised to power 2 here. So what we have to do, just times this one by this one. 5.6 times 2.1, you get what you get, and raised to power 2. All right. Then let's say you now have divide. You have finished. You now have 2. Maybe you have 5.6 times 10 raised to power 2. Okay, over 2.1 times 10 raised to power minus 4. Let's say this is what you now have. Remember, divide in indices. Divide usually turns to what? Minus, right? So what do you do here? When you are solving, just do this one separately. You divide this by this. Then for this raised in power, what do? You put minus at the center. So here is plus. So plus 2, put it in brackets. Then minus, because of this divide indices, minus brackets minus 4.